In section 5.1, we're going to continue using the fundamental trig identities, except now we're going to add a few more, and we're going to use them a little bit more purposefully. So in the table, these identities are the reciprocal and quotient identities, which you will recall from chapter 4. Okay, over here we have the Pythagorean identities. The main one is sine squared u plus cosine squared u equals 1. Many of you have already started using rearrangements of the Pythagorean identity. For example, if I subtract the cosine squared to the other side, I get 1 minus cosine squared u. So if you see 1 minus cosine squared u, you can make the substitution sine squared u. And the same is true with cosine squared u. If I subtract the sine squared, it looks like this. And you can make that substitution right away, as many of you have already started doing. The next two Pythagorean identities, remember, are derived from the original. So if I start with the original one and I divide everything by cosine squared, I end up with tangent squared, 1, secant squared. And if I go back to the original one and I divide everything by sine squared, I get 1, cotangent squared, cosecant squared. These are the ones we are already familiar with. Okay, now we have the even-odd identities, which we have thought about, but we haven't formalized them as identities. Okay, I'm going to show you what they are doing, even though I'm not proving it yet because we don't actually know the identities required to prove this. Okay, but I can still look at it. If I imagine this is u, this is positive u. If I went negative u, it would be down here. Okay, and if you recall previously, we compared the cosine and sine values of u versus negative u. So if I look at u and negative u, they have the same x coordinates, but their y coordinates are opposite, which is why if I do the sine of negative u, I get the negative sine of u because the y value is the opposite of the original. The cosine of negative u equals the cosine of u because the x's are the same. And then the tangent of negative u equals the negative tangent of u because it's y over x. Since the y's change signs, the tangents change signs. Okay, the next identity we're going to introduce are the cofunction identities. Okay, and again, we don't actually know the identities required to prove this. We will later in this chapter. So I'm just going to show you geometrically why this is true. Let me think. I'm going to call this u. Okay, and the reason I'm going to do that, because it's geometric, instead of pi over 2, I'm going to think of pi over 2 as 90 degrees. So if this angle is u, this angle up here is 90 degrees minus u. Okay, so if I think about this real quick, and you don't need to write this down, I'm just showing you. I need to give these sides. How about x, y, r? Okay, so if I do the cosine of u, that would be x over r. If I do the sine of 90 degrees minus u, I would also get x over r, okay, because I'm just using the opposite angle. So that's basically what this is saying, okay? And geometrically, it makes sense because you can see that the sides switch with each other. Okay, today we're just going to practice simplifying trig identities just like we did previously. The only difference is we're adding some of these new functions that we had not previously used. Okay, so for this first one, it says simplify cotangent x sine of negative x. Just like before, the main strategy we use is rewriting things in terms of cosine and sine, unless you see something else useful you can do. So for cotangent, I'm going to rewrite that as cosine x over sine x. Okay, so for the sine of negative x, if I go back to the even odd, the sine of negative x is the same as negative sine x. So I am going to change that to negative sine x. Okay, and I did want to do that because if I had kept it as sine negative x, it would not be able to cancel. But now that it's negative sine x, I can cancel the sine x and keep the negative, which will leave me with negative cosine x, which is a nice single term. I got rid of any fractions. I canceled anything I possibly could. Okay, I'm going to go ahead and try to simplify number 2. Just like we were doing previously, I'm just adding a few identities to it. Okay, let me see. The cosine of pi over 2 minus x, that's a cofunction identity. Okay, so the cosine of pi over 2 minus x is going to be the same as the sine of x. And the only reason I change it is because it's more likely to cancel later, or it will be easier to work with later. Okay, I'm going to go ahead and bring down sine x is nice, plus cosine x is nice. I'm going to rewrite cotangent as cosine x over sine x, because now at least I have everything in terms of cosine and sine, and I can try to work with it from there. Okay, there's more than one way to do these. I'm going to go ahead and simplify the fraction first. Yours could be different as long as you're showing all the steps, because these are like proofs. The steps are what is important. So I'm going to make this sine x plus, and I'm going to consolidate that fraction. Cosine times cosine is cosine squared, x over sine x. Let's see, now I think I'm going to go ahead and distribute this sine x. Sine times sine is sine squared x. Okay, and if I do sine x times cosine squared x over sine x, the sine and the sine x cancel. So I'm left with cosine squared x. Okay, and then once I get here, sine squared x plus cosine squared x is a Pythagorean identity. So this simplifies all the way down to just 1. And your steps could be different, but you do need to make sure you're showing all your steps because that's what's important. Okay, for the next two, I'm just going to show you some strategy that is sometimes used for these. Okay, so for number 3, it says simplify sine x minus sine x cosine squared x. Everything's already in terms of sine and cosine. But I can see that there's a common factor. They both have a sine x. So I'm going to factor out the sine x. Okay, if I divide out the sine x, I get 1 minus, and if I factor out this sine x, I'm left with cosine squared x. Okay, let me see what I can do with this. Okay, I can make the substitution for 1 and change it to sine squared plus cosine squared, or I can notice that this is a rearrangement of sine squared x plus cosine squared x equals 1 and change it to sine squared x. However you do it's fine with me. Okay, and then if I do sine x times sine squared x, that turns into sine to the third x. So that's the nicest, simplest way to write my simplified answer. Okay, for number 4, let's see, I have two fractions. They both have cosine sine, so I need a common denominator. And sometimes it looks worse in order to get better. Okay, so I can see that one fraction has 1 plus cosine x, the other one has sine x. I want to make them match. So I'm going to multiply the first fraction by sine x over sine x. And the second fraction, I'm going to multiply by 1 plus cosine x because I want them to have a common denominator. Okay, now I'm going to rewrite the denominator. I'm going to leave it in factored form because sometimes something cancels, and if I leave it in factored form, it's easier for me to see what's going to cancel. But I am going to distribute out the numerator to see what's happening there. So sine times sine is sine squared x plus cosine x times 1 plus cosine x is cosine x plus cosine squared x. Okay, now I'm going to look at the numerator and see what I can do with that because I know eventually I want this to cancel. Okay, I see that I have a sine squared x plus a cosine squared x, which means those two should equal to 1. So I'm going to make that substitution. I make that into a 1, and I'm going to bring the plus cosine x down. My denominator, I'm just going to keep it the same. I kept it in factored form again because it's easier to tell if something's going to cancel. Okay, now I can see that the 1 plus cosine x is going to cancel with the 1 plus cosine x, which means I'm left with 1 over sine x. And then when possible, I rewrite without a fraction. So I'm going to rewrite this as cosecant x. Okay, and again, your steps could be different, but you do need to show all the steps because this is like a proof. Okay, with these problems, we're going to just practice rearranging things in different ways using trig identities. For the first ones, we're going to factor them, which will be useful when we're solving these equations. Let's see, tangent squared x minus 1, that's a difference of squares. Okay, when you're factoring this, you don't need to rewrite it, but think about this as u squared minus 1. I know that would be minus 1 and plus 1, but instead of u, I'm using tangent because it's tangent squared x. So it's really tangent x minus 1 times tangent x plus 1. And that is all I can do to factor it. Okay, and right now we're just practicing this, but once we start solving these, we will be using that to help solve them. Okay, I'm going to factor 3 secant squared x plus 2 secant x minus 1. And remember, when you're thinking of the numbers, think of this as 3u squared plus 2u minus 1, but really u is secant squared or secant x. But when I factor it, I'm looking to make those coefficients work. Let's see. Okay, use whichever method you normally use to get this, but instead of using 3u and u, I'm going to use 3 secant x and secant x. Okay, if it would factor more, I would factor it more, but that's all I can do. Okay, for number 7, it says secant squared x plus tangent x minus 7. I can't factor it if it has two different trig functions in it. So I'm going to have to make a substitution. Because I see there's a squared, I'm going to make the substitution at the secant squared because of the Pythagorean identities, and I know that there's something squared which I can make a substitution for. Okay, if you check back on your Pythagorean identities, secant squared equals to tangent squared x plus 1. Okay, and then I'm going to bring down the rest of this and simplify it before I factor it. Okay, but now at least everything is in terms of tangent, which means it should be easier to factor. Tangent squared x plus tangent x. Okay, and then I do have a positive 1 minus 7, so I'm going to make that a minus 6 at the end. Okay, now I can go ahead and factor this. Okay, remember, treat this like u squared plus u minus 6, so that's going to be plus 3 minus 2. And instead of u, I use tangent. Okay, this one, factor sine squared x plus cosine x plus 1. Again, it has two different trig functions in it, which is no good, so I need to make a substitution. Okay, where I see sine squared, I'm going to use that for my substitution because I know I can use a Pythagorean identity. Sine squared turns into 1 minus cosine squared x. And then I will bring down the plus cosine x and the plus 1. Okay, I'm going to rewrite this in standard form. So that will be negative cosine squared x plus cosine x plus 1 is 2. Okay, now I'm going to factor it. If you don't mind factoring it with the negative in the front, you're welcome to factor it with the negative in the front. I'm going to factor the negative out, so it's easier for me to factor in my head. If I take out the negative, this is negative cosine squared x. Now this is a minus cosine x, and this is a minus 2. Okay, I factored the negative out, but it's still there. So this is still equivalent to this. Okay, so you can factor it out, but make sure it's still there because it would be significant if I were trying to graph this or do something else with this. Okay, I'm going to keep the negative in the front. Okay, remember this is like u squared minus u minus 2. So what am I trying to get? I'm trying to get negative 2. So negative 2, positive 1. Instead of u, I'm using cosine. Okay, and if you did not factor out the negative, you would have a similar factorization as this one, but the negative would be distributed into one of the factors. Okay, now for number 9. It says rewrite it so it's not in fractional form. It does not say it needs to be simplified. It doesn't have all these other rules, but it does say I want to get rid of all the fractions. Okay, I'm going to start with the expression that's on it. Okay, I don't see anything obvious I could do to get rid of the fractions. But I do see this 1 minus cosine x at the bottom, which is asking me to multiply by the conjugate of it. Okay, since it's 1 minus cosine x, I'm going to multiply by 1 plus cosine x. And this is a common strategy. So whenever you see something like this is often how you will do it. Okay, I am going to go ahead and multiply this out. Let's see, on the numerator, 1 times 1 plus cosine x is 1 plus cosine x. Okay, on the denominator, 1 minus cosine x times 1 plus cosine x is 1 minus cosine squared x. Okay, and we like this because we recognize this as a Pythagorean identity. It's rearranged, but it's still a Pythagorean identity. And the purpose of doing the conjugate is to create that Pythagorean identity at the bottom. Okay, 1 minus cosine squared x is really equivalent to sine squared x. Okay, now what am I trying to do? I'm trying to rewrite this in non-fractional form, but it does not say they have to be a single term like when I'm simplifying. So I'm going to split this up, and then I'm going to work with it. Okay, let's see. 1 over sine squared x is cosecant squared x. So my fraction's gone there, which is great. Okay, I'm going to split this sine up. Okay, that's still the same as cosine x over sine squared x, but now I can rewrite them each without a fraction. This will be cotangent x, this will be cosecant x. And because the directions just told me to rewrite without a fraction, I'm done because I've rewritten it and now there's no more fractions in it. Okay, the last thing in this section is the trigonometric substitution. It says use x equals 3 tangent theta, 0 is less than theta is less than pi over 2 to write 9 plus x squared as a trigonometric function of theta. They just want you to make a substitution. They're trying to get you ready for polar coordinates. They do tell you 0 is less than theta is less than pi over 2, which tells you you're in quadrant 1. So it's just trying to keep things positive. I think they're trying to make it easier for you. Okay, so since it says x equals 3 tangent theta, where the x's, I substitute in 3 tangent theta. 9 plus, instead of x, 3 tangent theta squared. Okay, and then we're going to simplify this. 9 plus 3 squared is 9 tangent squared theta. I can see that nice little 9. So I'm going to go ahead and factor it out. Okay, and then I'll substitute it first. Okay, 1 plus tangent squared theta looks like a Pythagorean identity. If you check the list, it turns to secant squared theta. And then when I square root 9 secant squared theta, because I'm in quadrant 1, I get positive 3. The square root of secant squared theta is going to be secant theta because I'm in quadrant 1, so everything's positive. Okay, that's what they're trying to get you to do. Okay, we're going to do 11, same way. Again, they tell you 0 is less than theta is less than pi over 2. They're just telling you quadrant 1 so you know that the answer is positive, so you don't have to think about the sign. Okay, let's see. 2 sine theta is x, so I'm going to plug that in right there. And if you know what to expect, then you just keep working till you get there. Okay, 1 minus sine squared theta is equivalent to cosine squared theta. And then when I square root 4 cosine theta, because I'm in quadrant 1, I get positive 2 cosine theta. And again, they're just trying to get you thinking like this, so when it comes up again in a later chapter, you'll recognize it.